So there are some transformations which can be used to convert the analog filters to a digital filter. For example, suppose if we have a first order digital filter, first order analog filter with transfer function as HA equal to 1 by 1 plus S, and let us say the cutoff frequency is omega C. Okay, so this is low pass filter of first order. Low pass filter of first order having pole at the omega C. Omega C is the cutoff frequency. Okay, and let us say that the cutoff frequency is given, that is, for digital filter the cutoff frequency is given 0.25 pi. 0.25 pi. Okay, and we have to convert this analog filter to a digital filter. Analog filter to a digital filter, and we need to use the bilinear transformation. Bilinear transformation. Okay, so as we discussed last time, that due to warping we can obtain the 3 dB frequency for Butterworth filter for digital filter as omega C the omega C for this will be 2 by Ts. Ts is the sampling frequency, and 10 of 0.25 pi, and omega C divided by 2. Okay, this is the thing. So when we calculate this, we will get its value to be 0.828. 0.828 divided by Ts. Ts is the sampling period. Okay. So what will be HAS then? HAS will be since it is the cutoff frequency for digital filter, so analog filter will have a cutoff frequency omega C, which will be this. Okay, so we can write it to be 1 by 1 plus S and Ts upon 0.828. 0.828. Okay, this will be the analog filter design. So corresponding to this, what will be the digital filter? Digital filter will be have transfer function as Hz, and if we are using bilinear transformation, then it can be obtained by putting S as equal to 2 by Ts. This transformation we have derived last time. this transformation last time we driven 1 minus 1 plus z raised to power minus 1. This is the transformation by linear transformation. And when we do this, we will get it to be 1 plus 2 by TS. Generally TS is, if TS is not specified, then generally we take this as unity. Okay, TS is taken to be 1 second, so it will be 0.828 and 1 minus z raised to power minus 1 divided by 1 plus z raised to power minus 1. Okay, this thing. This will be the transfer function for the digital filter. And when we simplify it, little bit of calculations, we will get it to be 1 plus z raised to power minus 1 minus 0.4659 z raised to power minus 1. Okay, we get this HZ. Next step will be to design this, implement this digital filter. So what is HZ? HZ is YZ, yani output, divided by XZ. It means input. Output divided by input. So what will be that? That will be 0.2920 plus 0.2920 z raised to power minus 1 divided by 1 minus 0.4659 z raised to power minus 1. Okay, this thing we get, when we cross multiply it, we will get YZ minus YZ z raised to power minus 1 0.4659 equal to 0.2920 XZ plus XZ z raised to power minus 1 0.2920. Okay, this is in Z domain. We can also get it in the N domain too. So the N domain, it will be like this: z raised to power minus 1. So it is first difference, n minus 1, yn minus 1, 0.4659 equal to, this will be, the same equation can be written in N domain too. Oh, sorry, xn plus 0.2920 x of n minus 1, x of n minus 1. This difference equation will be a digital system which can be implemented by the delay elements. Okay, like this. Suppose this is input yn xn multiplied with 2920 xn okay, this thing will be this, and then our difference, if d is the delay difference, then it will be multiplied by 0.2920, okay, like this. This thing is this. Right hand side is implemented, and it will be your yn, and this yn will be getting delayed, and then it will be multiplying with 0.4659 here the term 0.4659. इससे यहाँ पे आउटपुट आएगा yn-1, and then you can put a summer here also, like this, like this, and you will get the digital filter design implementation. This is how the digital filter can be implemented. This block diagram will be giving you how the digital filter can be implemented by using this difference equation. Okay. As you know, this is the implementation where there is a feedback from the output side to the input side due to this connection. This connection is regarded as a feedback. Okay, and as we know that whenever the system has a feedback kind of a thing, then its impulse response is infinite. And therefore this type of implementation is regarded as IIR implementation. IIR means infinite impulse response digital filter. IIR digital filter. IIR digital filter stands for infinite impulse response, because there is a feedback in the from output to input. Signal is going output to input, hence there is a feedback and it will have infinite impulse response. Therefore this kind of design is referred as IIR digital filter designs. Okay, so by these transformation, bilinear transformation and inverse invariant transformation, these are the examples of IIR digital filter design. Now we will be discussing finite impulse response digital filter. Okay, where the there will be no feedback, so that it goes to the forward direction only. The signal flow goes to forward direction, hence the output is not depending upon the present or the past outputs. Okay, it is only depending upon the inputs and the past inputs. Okay.